talk about the crystal structure of graphite. Now, the natural graphite that we were talking about, that is available in two crystallographic forms. So one of them is known as the hexagonal graphite. That is something that we mostly talk about. This is the the more common form of graphite, and the other one is also known as rhombohedral graphite. Now it is called rhombohedral because it has a crystal structure which is rhombohedral. So we are going to also learn about that. Okay, so let's first talk about the hexagonal graphite or the common graphite, and the crystal structure of this graphite looks like this. So as we have also previously learned that it has this A type crystal structure. Okay, so now you see this this box that I have shown there. That actually shows the unit cell of this graphite. So we are not taking the we are not taking the entire hexagon as a unit cell. We are rather taking just we are connecting two atoms of one carbon hexagon, and then one atom of the neighboring hexagon, and that is how we are forming. And we are also, this is also important to see that we are taking not two but three layers, and then we are forming a unit cell. Now there are different crystal parameters. You see the value of A, which is so I have this here. So if I have, this is my one hexagon. If the value of A is the separation between this and this. So this here, if you draw a line, that is going to be your value of A. Okay. Now also the other values, for example, the value of C. Now there we are talking about three different layers, and the value of C is between the two A layers. So it is ABA, right? So between A, and the B layer, we have it in between. But that's not, but the unit cell contains two A layers. It connects two A layers. Now this value of C is 0.67 nanometer. But if somebody asks you what is the separation of layers in a graphite crystal, then that is not 0.67, that is half of 0.67, because that is, we have one extra layer in between. Okay, so now there are one also interesting thing is that is graphite crystal a hexagonal closed packed structure? So you know what is a hexagonal closed packing, or the closest packed structure, which takes a hexagonal shape, that actually has the closest packing by volume for any spherical objects. So that is how it should be. But that would be possible only when you have the closest packing, which means that you have one layer exactly on top of that, touching the atoms. You have another layer, the B layer, and then again exactly without any space between the two layers, you have the layers stacked on top of each other. That would be the closest packing. So here I have shown it with the with this arrangement. So you have the layer number 1. So let's say this is your A layer, this is your B layer, and then this is again your A layer. So it's like a pyramid of balls. So this is hexagonal closed packed structure. In the case of graphite, you have hexagonal crystal structure, but it is not the closest packed structure. The layers are slightly separated. They are not exactly on top of each other. Can you guess why does this happen? We know why does this happen, right? Everything in carbon, everything in graphite, all caused by this unhybridized p orbital and the electron that is in that unhybridized orbital, because that electron forms a cloud, it is delocalized, it does all kinds of funny things. So because of that electron, now you have the clouds of both of these layers. So there is a little bit of gap. It's not the closest packing, and that is why you don't call graphite structure as HCP structure. You just call it hexagonal crystal. Okay. So also in the case of an ideal hexagonal crystal, HCP type arrangement, if you do the geometric calculations, you will find that the value of C should ideally be 1.633 times that of A. But in the case of graphite, that is not the case. As I already mentioned, you have it slightly higher. The separation is slightly higher because of our electron cloud and the unhybridized orbital. Okay. Now other constants, other lattice constants. A equals 0.245 nanometer. Now in this image, where do you see A? Here it is. This is, as I said, between any atom number 1 and 3 of any hexagon, that is 0.245 246 nanometer. You see A, you see C. Where is B? B is actually here. We just don't mention B because B equals A. So we are always talking about either A or talking about C. B is there, but B is, because it's equal to A, then we don't specifically mention its value. Okay. Now the separation between two layers, as I said, between A and B layer will be 0.335 nanometer, which is half of 0.67. Okay, so actually whenever you see these transmission electron microscope images, and I had also shown you these lines, you see the crystallographic lines that if you take the cross section, those are basically you see the separation. In the case of perfect graphite, the separation should be 0.335 nanometer. Okay. So now the bond length. So if I talk about the two adjacent carbon atoms, then the bond length is 0.142 nanometer. Remember that this is actually much shorter than what you have in the case of diamond. Even though diamond has, it has sp3 hybridization, the electronegativity of your bond is higher in the case of graphite, which is caused by the fact that you have more S character in the hybridization. And that is why the electronegativity, because of that, you have a shorter bond length, which means this is a stronger bond. Shorter bond length will always give you stronger stronger molecules, right? Because the closer they are, the more tightly bound they are. So shorter bond length means stronger. So that is why if you take a single layer of graphite, which is graphene, that in principle would be stronger than diamond, because the bond length in the case of diamond is 1.54 angstrom, but in the case of graphite it is 1.42 angstrom. So that is why this is a shorter bond length. We'll also discuss it further when we talk about diamonds. Okay. Now another interesting thing is that there is an atom that I have marked with the red color, with a solid red ball, and there is a dashed line going up. What does it indicate? It indicates that this is your atom which has its neighbor directly on top of it in the next layer. Okay, let's see another one. This atom also has a neighbor on the top layer. Then the third one, this one also has a neighbor in the top one. However, if I take the other three atoms of this hexagon, they do not have any adjacent atom in the layer right above them. They have to go all the way to the next A layer to find their neighbor. Similarly, this will happen for the other two. What I am trying to say here is all 6 atoms of the hexagon are not identical in the case of a graphite crystal, and in fact that is the reason that we did not take all 6 atoms in our unit cell, because unit cell basically should be the smallest repeating unit. So all atoms there have to be identical, and that is why. So remember that 3 atoms of this hexagon, alternating 3 atoms, are different from the other 3 because of the fact that you don't have their neighbors in the adjacent layers. Okay. Now the space group. So we will discuss space groups and point groups later on. The space group of graphite, you can see over here. We'll discuss that. This basically tells you about symmetry elements, and that I will cover separately. Okay. Now other properties of graphite. I have just written 2600 Kelvin, but you know that also. This is stable up to very high temperatures. Okay. Yeah, so several gigapascals. Actually, I did not mention the value of gigapascals. You can see that in the phase diagram. Okay. Now the properties of graphite in general are what is known as anisotropic. Anisotropic means you have different values in one direction compared to the other direction. You can see that there is so much difference in the crystal structure when it comes to the in-plane graphite structure and the perpendicular to the plane graphite structure. So it is very obvious that we are going to have different sets of properties, whether it comes to electrical conductivity, whether it comes to thermal properties, whether it comes to any other magnetic properties and so on. You will always have difference when it comes to what you have in parallel to the C axis and parallel to the A axis of the crystal. So this is just an example that the thermal expansion coefficient is very much different in both of these directions. In general, this is a very interesting thing about graphite also, that you have very high anisotropy, which means you have very different crystal structures in very different properties, parallel and perpendicular to the basal planes. Okay, now there are two important parameters that you need to learn. They are known as LA and LC. What is LA, LC? L actually is length. Length in A direction and length in C direction. Now, what do we mean by length? Length of not a single crystal, but length of a crystal light. We talked about what is crystallinity when we measure how much portion of a certain solid is crystalline and the rest of it is non-crystalline. Then how do we measure it? We need to somehow measure the size of these crystallites. Also, when you're doing the mining and the ore processing and so on, what you do is you want to know what is the largest crystal you have. So if you take a crystallite, then how do you measure it? You measure, because again, the anisotropy of graphite, sometimes you will have very high stacks. So several layers of graphite stacked on top of each other. However, the diameter or the actual size, if you look at it from the top view, that might not be so much. That might be very small. On the other hand, sometimes you can have very sort of horizontal crystals. So the layers are not so many. But at the same time, the spread is horizontal direction is a lot. So there are these two parameters that have been defined. These are the standard parameters. Based on this, you will say it is good crystal, bad crystal, and in a lot of crystallographic and diffraction studies also, these are the two parameters that you use, LA and LC. So now I have shown here, let's say this gray color, this is a stack of graphite crystals. They don't need to be hexagonal, by the way. It's just, I have shown that, let's say all the sheets are hexagonal. Now LC is this, what is known as the stack thickness. Stack thickness. That is known as the LC. And LA is something, if you considered that this entire crystallite was a sphere, then what would be the diameter of that sphere? That is known as LA. So it's not just a single layer, it's not a 2D structure, but it's more of, if you consider the an equivalent sphere for every crystallite, because every crystallite has slightly different shape. So if you considered an equivalent sphere, then the diameter of that would be your LA, or the crystallite diameter, and the LC you already know is the stack thickness. Now, how many carbon atoms do you have in one unit cell? So you see the unit cell in this picture, and now you just need to count how many total atoms you have in this unit cell. There can be different ways of calculating it, but there is one way which I personally found more convenient, and this is probably similar to what you traditionally do, count the corner atoms, and you see how many atoms or how many unit cells share these corner atoms, and then if we have anything in addition to that. So now here we have to calculate this for 3 layers. So A, and then B, and then A layers. But let's see how we can do this. Okay, so the unit cell that you see, it will also have other unit cells surrounding it, and it will also have the same number of unit cells on top of it. So let's see, this is with the red color, I have drawn one neighboring unit cell. Now you're going to have not just one, but more neighboring cells. So if you think of it, how many unit cells would share the corner atoms? If you take the corner of one of these, they are not squares or rectangles, but this geometry. Now, if you take one of the corner atoms, how many unit cells are actually sharing it? So from here you see that one atom is shared with 4 unit cells. And then you also have 4 on top of it. So each corner atom is shared with 8 unit cells. Okay. However, if you have a cubic structure, or if you have an FCC structure, for example, then each unit, so it is 1 by 8, 1 by 1/8 atom is shared at each corner of each cube for each atom. So each of these 4 atoms contribute equally into the to your unit cell. But is that the case with our unit cells here because of the hexagonal geometry? So let's have a look at the corner atoms alone. So for now I forget that there is anything in the center or in the middle of it or any other atoms. We have these 4 corner atoms. Okay, and now the unit cell looks something like this. Now you need to calculate what are the angles and how much fraction of a single atom is being considered for your calculation of the total number of atoms. Okay, so now if you will also draw the connecting hexagons, then you will figure out based on the angles, you will find some 120 angles and some 60-degree angles, and based on that, by calculating the geometry based on simple triangles and hexagons, then you will figure out that this region, the region with the blue color, the shaded region, one of them has 1/6 of an atom, and the other one has 1/3 of an atom. So now we have 2 atoms contributing 1/6 each and 2 1/3 each. Okay, now we have this for the top layer and we also have this for the bottom A layer. So altogether how many atoms do we have then? Then afterwards we'll also consider the center atom also. So in the A layer, if you want to count the number of atoms, you have these 1/3 and 1/6, 2 each. So I multiplied them by 2 and added them. However, now I have divided the entire thing by half because you also have something on the top. So that we had not factored in till now. So if you divide it by 2, then altogether these 4 atoms to each individual unit cells in one layer would contribute half an atom. Okay. Now half an atom will also come from the center atom, which is circled with the black color. That is not exactly at the center, but that is not shared at the corners. So half of it, because half goes to the top layer. So half of it also comes from there. Okay, so half plus half would make it 1 atom in each A layer, and because we have 2 A layers, then we have 2 atoms coming from the A layer. Okay, now what about the B layer? So now for understanding the atoms and the geometry in the B layer, it's better to look at the top view of this crystal structure. So here is the top view. We have one layer and on top of that we have another layer. Okay, now let's draw our unit cell. So it looks like this. Now here easily you can see how many atoms do you have. So number 1 and the one behind this particular atom. So these 2 are from the B layer. So you have 2 complete B layer atoms. They are not shared by the unit cell on top or bottom, so we don't need to worry about that. So we have 2 atoms now coming from the B layer. Altogether we have 4 atoms in the graphite unit cell. Okay, now coming to another aspect of crystal structure, Miller indices. So I expect that you have learned something about Miller indices in your basic material science courses. Now we know that how to calculate Miller indices. Probably you know. If not, then I will briefly let you know. For the planes we are calculating the Miller indices. So let's see, we start with a certain plane. Now we have this A1, A2, A3. These are the different lattice vectors. Now we start with this basal plane. Why do we call it basal plane? Because that is the base of the hexagon. So all these planes which are parallel to the base, they are called basal planes of graphite. So we take one plane from here. Now you need to calculate what are the intercepts. The first step of calculating the Miller indices for the planes is that you take the intercepts that plane would make on all 3 lattice vector. Okay, so on lattice vector A1 and A2, now it will have infinite, and so it is parallel to them, it will never intercept them. So you have infinity, and now you have the plane at C/2, because your entire unit cell has 2 A layers. So this is C/2 or half on the C axis. Okay. Now the second step of calculation is that you take the reciprocal of these intercepts. So for infinity you will have 0, and then for half you will have 2, and then in the case that these are not integers you will typically multiply it with any integer in order to make sure that these are the smallest integers, but in this particular case we anyway have 0, 0, 2. So these are the Miller indices for our planes, for the basal planes. Okay. Now in general, these are also written as 0, 0, L planes. So that is the more general form. This is very important in the case of graphite. When we learn the characterization technique, not just for graphite, for any carbon material, because in all carbon materials, ultimately we are trying to find out the graphitic regions, what is the crystallinity. So whenever we characterize these things, there should be some signature pattern of graphite. And that signature pattern actually comes from this arrangement of layers, which even differentiates between multilayer graphene and graphite, because in the case of graphite, the layer separation is smaller than what you have in multilayer graphene. So this 002 plane separation or 00L plane separation, that is very important parameter when you understand the crystal structure and when you characterize the carbon materials. Okay. Now also we can take another vertical plane. Now you can do the calculations by yourself, but I have already shown that this would be your 110 plane. Okay. Now these were the Miller indices. In the case of hexagonal crystals, you also have another parameter that defines your crystal, which is known as the Miller-Bravai indices. Now Miller indices have H, K and L. In the case of Miller-Bravai, you will have H, K, I and L. So there is a fourth additional, this is actually a redundant lattice vector A3 which is added. And now you also have this additional index which is known as I. Why we call it redundant? Because you can actually obtain it by adding and then having a minus sign. So minus H plus K equals your I. So for example, for the 001 planes, you will have the Bravai-Miller indices as 0001. Because you add H plus K, in this case it's all of it is 0. Okay. Now if I take another plane, the 110 plane that we were talking about, here the value of I will be minus 2, because it is minus of 1 plus 1. And minus 2 is written as a bar, 2 bar. This is just a common practice in the case of crystal structure. So here you will have your MB or Miller-Bravai indices as 1, 1, 2 bar and 0. So don't get confused if you see these 4 indices. Basically the fourth one, the redundant one, is added in order to include all the symmetry elements, to make sure that we can completely explain the crystal, because you see the hexagonal crystals have more or different symmetry elements compared to the cubic crystals. So in order to justify that, we add this fourth index.
Okay, so what we are going to do now, we are going to draw some of the planes in a graphite unit cell. So first let us draw the graphite crystal. Let's see how quickly we can draw this. Okay, so first we draw these, the unit cell itself. And then what we are also going to do is we are going to complete the hexagon, because that will give us a better idea of where do our planes lie. So first of all, where are the atoms? Number 1, 2, 3 and 4. And there is one atom that lies here. Similarly, for the bottom B layer, you can draw these atoms. So you should remember that the corner atoms are not completely within the unit cell. They do not have 100% contribution. But the one in the middle, that is completely there in your unit cell. Of course, it is shared with the top and bottom layers. Okay. Anyway, I was saying that I'm going to also tell you the entire hexagon. How does it look like? So if we had the entire hexagon here, then we would have, it would look something like this. This is not a part of the unit cell, remember. I'm just showing it to you because I'd like to, I would like you to be able to relate to the entire hexagonal geometry when we talk about or when we draw certain planes. Okay, so this is your graphite unit cell. Now what are we going to do here? What we are going to do is we are going to draw some of these planes. So number 1, 002 plane, which we already have seen multiple times. 100 plane. Then let's also draw 110 plane, 101 plane. What else? 112 plane also we can draw. So these are actually some of the planes that you will see when you characterize graphite. For example, using X-ray diffraction studies. So we will talk about X-ray diffraction later, but it is important for you to understand where do these planes lie in your graphite unit cell. Okay, so these are some of the planes. In addition, you will also sometimes see what is known as second order peaks, so 004, 006, and you will also see, for example, 102, 104 up to 1006 planes, but the 5 primary planes that we are going to draw here. Okay, so first of all, yes, before we draw the planes, we should also mention where are the units, where are our lattice vectors. So you know that already. We have lattice vector C and we have A1 and A2. Now A3 I'm not drawing here because anyway you know that it is sorry, this is C. A3 is you can always calculate it as a linear combination of A1 and A2 anyway. Okay, so well, now let's start with the first plane, 002 plane. So 002, you already know it lies somewhere here, so we will not go into the details. You know that 002 planes are here, right in the middle of your C lattice vector. Okay, now let's get started with other interesting planes. So how about plane number 2? That is 100 plane. Okay, so now you know already that when I say 100, that basically means you know how to calculate the Miller indices. 100 basically means that the intercept along A1 is 1. And 0 basically means that there is no, the plane is parallel to A2 as well as it is parallel to C axis. So now that is not very difficult. First of all, let's draw a line parallel to A2 and also draw a line parallel to C. Now this is our plane, right? This is an easy one. So this plane is basically, this is basically your 100 plane. Okay, so let me also mention here, this is 100 plane. Okay, so now let us try to draw 110 plane. Okay, 110, what does that mean? So 110 means, number one, on A1, along A1 you have intercept 1, also along A2 you have intercept 1, but the plane is parallel to the C axis. Okay, which basically means this is the diagonal plane. I hope you can see this. Along, so it is parallel to the C axis, which means it will look like this. And then this diagonal plane is basically going to be your plane of interest. Okay, so this is the plane which is your 110 plane. Okay, now moving on. So this is also done. Now we move on to 101 plane. So how will you draw 101 plane? Again, this is over here, the intercept is 1. It is parallel to A2 because the intercept is now 0. However, there is intercept 1 on the C axis. Okay, and this is parallel to A2. So basically, this is the plane over here and over here. If you can, I hope you can see in the same diagram, this plane. Okay, so this plane basically is going to be your 101 plane. Okay, so let me write down, this is your 101 plane. Okay, now what else do we have here? We just have one more plane left, which is 112. So 112 is actually rather easy. Whenever we have 2, that means the intercept is half. Okay, and over here 1 and over here 1. Okay, so this is an easy plane to draw. This here, here and here, this particular plane is your 112 plane. Okay, so now we are done with most of our plane in the graphite crystal. So another related quick exercise, you see that I have drawn one sheet of hexagons in black color, and now I'm trying to draw another one on top of it in blue color. Okay, so this is how your 3D graphite looks like. This is how your graphite, hexagonal graphite crystal looks like. Okay, Now if I, right now what do we have here? We have our lattices, the unit cell, sorry. This is how we select our unit cell. So we go from this point, and we select our unit cell like this. Okay, we have atoms number 1, number 2 here, 3 and 4, and then we have one atom sitting here. This is our first type of unit cell, right? Why did we do that? Because we have also, you remember that we have A and B, so we have two types of atoms, right? So 2 atoms or 3 atoms of the hexagon are different, in terms of, they are not chemically different, by the way. So they are just not equivalent in terms of crystal geometry. So A and B type of atoms we have. Now can we also have A and B type of atom of the same hexagon in one unit cell? Okay, so basically this and this. So if you see the blue hexagon, then you have the A and B type atoms of the same hexagon. My question to you is that can we select a unit cell somehow such that we can accommodate these two atoms, so these two fall in the center. So again we have an A type atom and B type atom. So the question is that can we also have this kind of unit cell for three-dimensional graphite? And this is the top view that you are looking at.